Okay, so here's what we're going to do. We are going to simulate this reservoir and try and find out what is the pressure in the fountain. And so we're going to set this up in EPANET just as a test to make sure that it gives us the pressure that we've already calculated on the whiteboard of 37.75 psi. And then we're going to change some things around, like we're going to see if we adjust the fluid properties, how does the pressure change? If we adjust the height of the water, like does that change the pressure? We'll play around with the length of the pipe and so on. I don't know what they're doing next door. It sounds like Santa's little workshop or something. They're cobbling shoes. All right, so here's what we do. We have EPANET, and across the top is a toolbar that allows you to start drawing elements. So the first thing is we're going to add a reservoir, and that's the symbol that looks like a tank that's open at the top. Now, a reservoir is different from a tank because a reservoir is bigger. It's much larger. Typically with a tank, it's going to have a smaller capacity, and so the water level may be changing over time, whereas a reservoir is really large. So you'll just specify a single elevation in the reservoir, whereas a tank we'd maybe need to specify how big the tank is so that in our system at night versus at the day, the water level in the tank could vary. So I'm just going to click on Add Reservoir, and then when I do that, you'll notice that the symbol changes. Like the cursor is changing to a target. Now in this window, this is a top view. So wherever I click, it's just going to be dropping the symbol for a reservoir. And even though there are X, Y coordinates at the bottom of the screen, you notice down here at the bottom it has X and Y coordinates. If you wanted to, you could georeference so that maybe you're drawing on top of a map. If you brought a picture into the background, we're not doing that. We're just going to create like a symbolic or kind of a schematic representation of where things are located. So I'm going to click, and so now that's my reservoir, and I'll change from the reservoir to the symbol to the left of that is Add Junction. And the junction is going to represent the fountain. And so just somewhere in the map, it doesn't matter if it's up here or down here, because remember, this is just a top view. And so it's not going to assume like that the pipe is sloped or anything like that, depending on where I click. This is simply just a symbolic representation of the system. So I'll click somewhere. Now I need to connect those two elements with a pipe. I've got my reservoir on the left, the junction on the right, where the junction represents the fountain. So now I'll connect them with this pipe, and I need to be pretty careful about where I click, because if I'm just in the proximity, it won't snap right to the object. We don't want the pipe to be near the reservoir. We want the program to know that the pipe connects into the reservoir. So I'm going to be certain that I click right in the middle of that symbol, and you can see the icon has changed to a pencil, and so I want it to be right in the middle of that junction. And now we have our third and final object in the model. Okay, so I'm going to change to Select Object with the menu across the top, just the arrow, Select Object. And if I double click on the reservoir, it's going to bring up the properties. So I'll double click, and so the first property you see, Reservoir ID, that's the name of the reservoir. And we're only going to have one reservoir, but if you had several, it maybe would make sense to give it a more descriptive name. You know, we could call this a Res-1. Now we could edit the coordinate system. We don't need to because the coordinates aren't going to mean anything. You could add a description if you wanted, you know, the street that it's on, you know, at the top of Jenkins Creek Road, something like that. Here's the important thing, and it has a star because this is required information to be able to do hydraulic calculations. The total head. The total head that we're going to enter is going to be the elevation of the water in the reservoir. Now, unfortunately, this system isn't telling us the units in the table that we've pulled up. But on the screen down at the bottom, you can see here it says GPM, gallons per minute. Now, head is going to be an elevation with units of feet, but the fact that this says GPM tells us that the unit system is in traditional units right now. And so length will be feet for pipe, diameter for pipe will be in inches, and then flow rate would be in gallons per minute. So right now we're in traditional units. It's possible to switch it to SI, and if it was in SI, like if this said LPM, meaning liters per second, then what that would mean is that the head now is, it knows that it should be meters of elevation. Okay, but it's in traditional units, so the head that I'm going to enter is 675.47, because that's the elevation that was described in this example that we're doing as a test. 675.47. So I have the total head indicated, and I can close that box. And now I'll double click on the junction, and the junction ID, it just says 2. So I'm going to call that fountain. It's just a little bit more descriptive of what it actually is. The elevation of the fountain is 588.36. Now there are some other things that we could put in here, and the most important that we're going to look at for now is base demand. There are two different ways that this system is calculating the hydraulic condition. One is steady state, meaning that the flow rates are constant, and then another one is an unsteady condition, where the flow rates, for example, in the evening when people are washing their clothes and flushing the toilet and doing laundry, all of that causes a lot of demand in the evening, and then in the middle of the night maybe there's hardly any demand. So we could set up this system to do like a fluctuating flow rate over the course of a day. And so that would be not the base demand. The base demand is kind of like what's the steady flow rate that's there all day long. So if you're just doing a steady state analysis, you put it in as the base demand. Otherwise, we would enter in a demand curve in a different spot. So for now, since our example says we want to analyze this in static conditions, static means no water is flowing, so we'll just leave this as 0 for now. So the only thing we did was we put in the elevation of the fountain. I guess we also changed the name. All right, so close that. And when you close it, it automatically updates the characteristics into the database that it's storing. Okay, the last element we want to double click and take a look at is the pipe. So double click on the pipe. Now the interesting thing is that, it's got a pipe number. It's number 1. We could rename the pipe if we wanted to, but we won't bother. But the thing that's interesting is it knows the starting node and the ending node. So look how it says that the pipe starts at reservoir 1 and it ends at the fountain. If I hadn't clicked close enough to the reservoir or the junction, then it wouldn't have snapped and it wouldn't know the starting and the ending relationship like that. So like if I did my analysis and there was no pressure in the pipe, maybe it's because the pipe isn't connected to the reservoir. All right, so length. This is 1,000 feet is the default. So it didn't determine that based on where I clicked. That's just kind of a placeholder value. And so our problem says the pipe is 175 feet long, 3-inch diameter, and has a roughness coefficient of 110. So length, 175. Diameter is 3 inches. And the clue that it's inches is the fact that it said 12 before. So that's a clue. It's a diameter in inches. So we'll move it to 3 inches. And then roughness, our problem says it's 110. This roughness coefficient is related to pipe friction. We haven't talked about how to calculate the effects of pipe friction. We will when we get to chapter 7 later in the semester. But remember, what happens is that when water is flowing through a pipe, the pipe is resisting the flow. And so the pressure is always decreasing because of that frictional loss. And so this roughness coefficient, it goes into a formula that predicts how much pressure is lost because of pipe friction. So the system, when the water is flowing, the system is going to use this roughness coefficient to determine how much of the losses are due to pipe friction. So those are all of the things that are starred, meaning that they're the required fields. The other things are optional, or the things that are in yellow are calculated quantities. So we haven't yet clicked the button and told it to find what's the flow rate, what's the pressure. We haven't run the simulation yet. When we do run the simulation, it's going to fill in these fields that are in yellow right now. All right, so any questions so far? Let's close the pipe window and let's run the simulation. It looks like a lightning bolt. So if you hover on that yellow lightning bolt, it says run. Click that and we get a little status message here. The run was successful. If you've made a mistake setting things up, you'll sometimes get a warning or an error message rather than the run was successful. I was getting an error message earlier when I was testing out an example that I usually go through in hydraulic engineering. I just wanted to make sure that this program could calculate the example. I was testing the software, and in the example I specifically have one location in the network where the pressure is negative, and it was giving me an error message because it detected in that particular location the pressure is negative, and that's a bad thing. If you've got negative pressure, then that means that the water is going to be sucking into the pipe. But anyways, we're successful here. So let's find out what is the pressure at the fountain, because that's what this is asking. This is saying find the pressure at the fountain in PSI. And we've previously on the whiteboard determined it's 37.8 PSI. So I just clicked on execute. I clicked on run. So now if you double click on the fountain again, it brings up the properties, and look at in yellow. So it tells me that the demand is 0 because I haven't told it any flow rates yet. I know the head at that location, and head is just a measurement of pressure, but it's in units of length. And the pressure, 37.74. We got 37.75. Yeah, so the tiny difference here is it's really insignificant. If you talk about 1/100th of a PSI, that's less than 0.1% error. And it's probably just because they have a slightly different unit weight. We're using 62.4. They probably have, 62.41. The unit weight that's built in is just very slightly different. So essentially, it's a perfect match. We should be really happy. So it's just as easy as that. That is what it does for the static conditions. Let's go through some of the bullet points on here. So we've already gone over how to draw the reservoir, pipe, and junction, and we've edited the parameters individually. If you have a complicated network, one nice feature is that you can pull up a table. Rather than, let's say if you had 10 pipes, it would be pretty tedious to double click on each one of them and change the length and look up what's the elevation and so on. Here across the menu bar is the table. And so if you click on that little icon for the table, and then here in the selection for columns, let's also turn on elevation and base demand. Then if you click OK, you'll notice it creates a table that has our junction and the reservoir. So we can see the elevation of each one of them, the pressure of the water at each location. So it's just kind of a convenient summary table of the properties, the result of our simulation. We have some options that we can change. One of them is that if you have a complicated network, it's important to see on the map the name of each junction. Let's say if you had a data table, if I gave you a handout and it said, location 1 has a certain elevation, location 2 has a different elevation, well, you'd want to be able to see on the map, what is the number of each junction. So we go to View, and in the View menu, there is the Options submenu. So View, Options, and then here under Notation, we can display node IDs. And when you click OK, then what it'll do is it'll put the name of each object directly above it. So if we had, a complicated network with several pipes and many junctions, then it would be useful for us to see the name of each one of them, just to keep things straight. That's one feature. Another thing is we can get into the settings, and we can change which formula it uses to do friction loss calculations. And that is under the Project menu and Analysis Options. It brings up this series of options. So one of the first things is the flow units. And you remember earlier I was talking about how we're in traditional units right now. We're working in the British gravitational system of units of feet, flow rate is gallons per minute, the diameter of the pipe is inches, and so on. If we wanted to change to SI, we would use that drop-down box and choose one of the SI unit system. And so traditional units are going to be cubic feet per second, gallons per minute. Anybody know what MGD stands for? Miller Genuine Draft. But it also stands for 1,000,000 gallons per day. And then IMGD is imperial million gallons per day. Believe it or not, the British, not only do they have, well, there's something called an imperial gallon, and it's bigger than a normal gallon. LPS is liters per second, LPM liters per minute, MLD million liters per day. So if you choose any of the SI units, then it would adjust everything else in the project as well.
Like all the numbers you already entered?
Well, that's the thing. It probably would screw stuff up. You'd have to start from scratch. And so, if you know you're going to be in SI units, my suggestion is make the adjustment to the units the very first thing that you do. That's a great question.
Where do you go to pick that up?
Good question. All right, so you go into Project, Analysis Options, and then the first thing that comes up is the hydraulics options in the analysis options. So we're going to stay in GPM. Now let me tell you a little bit about the head loss formula. There are three alternatives under the head loss formula. The three options are H-W, and that stands for Hazen-Williams. The roughness coefficient that we have of 110, that's a Hazen-Williams roughness coefficient. And the Hazen-Williams equation is just an approach that it's pretty simple to apply. It's not super accurate, but it's fairly accurate. And it just predicts how much energy is lost when water is flowing through a pipe at a certain velocity. And so it's going to calculate the velocity of the water moving through the pipe, and then how much pressure is lost for every foot of pipe is estimated with the formula that's in the Hazen-Williams equation. The more accurate equation that's more sophisticated but a little more complicated to apply is DW, Darcy-Weisbach. So we'll use Darcy-Weisbach equation a lot next semester when we're in hydraulic engineering, because when you've got a computer doing the calculations, it doesn't matter to us if it takes an extra half second for the solution to converge. The improved accuracy is worthwhile, it's important, so we'll usually next semester switch it from Hazen-Williams and we'll go to the more sophisticated and accurate Darcy-Weisbach equation. The last option here is the least accurate. This is the Chesney-Manning equation. And frankly, I don't even know why they bother to include the Chesney-Manning equation, because Manning's equation is great for open channel flow, but it's not accurate for pipe flow. So we shouldn't use it, and we won't use it for pipe flow. So let's just leave it on Hayes and Williams for now. Now look here under specific gravity. Does anybody remember what the definition of specific gravity, or SG? Do you remember what is the formula for that?
Weight of a fluid over weight of gravity? No, water. Yeah, water.
So weight of some fluid divided by the gamma of water. So it can be either unit weight or it can be density. Either one. All right, so right now it's set to 1. So that essentially means that it's assuming the fluid is water. But if we were wanting to simulate mercury, then what we would do is we would change the specific gravity to 13.56. And so by doing that, now the system is going to know to use a specific gravity that's 13.56 times that of water. Or if we had oil, for example, we know oil is lighter than water. That's why it floats on top of water. So if we had some oil like SAE 30, maybe we could go to the back of the book. For instance, I think your textbook in table A5 mentions the specific gravity of water at different temperatures. So you could look up what's the specific gravity at 120 Fahrenheit relative to the specific gravity at 40 Fahrenheit and find out some multiplier to add in here for the specific gravity. So that's going to change what the system knows is the density of the fluid. So that's one thing. The other thing it allows us to do is change the viscosity. So the viscosity of water is 1 times 10 to the minus third Newton seconds per meter squared. So if we had something other than water, if we had oil or glycerin or some other fluid, we'd look up what is the viscosity of that, divide it by the viscosity of water, and we're going to get some fraction, and we could type that fraction in here to relative viscosity. So I just mention it to point out that this system can be used for fluids other than water. You could design an oil pipeline, or if you're doing this on a chemical plant, you could simulate the pressure changes of whatever this fluid is through the chemical plant, as long as you adjust the specific gravity and the viscosity of the fluid appropriately. The rest of these options are mostly about how accurate you want the system to be when it's manually iterating. It goes through a computational process of energy balance, and it's kind of like a trial and error approach. It's trying to get in this network the flow rate to equal at each junction. They want to look at the flow in and the flow out. So we'll go into all the hairy details of it next semester, but the rest of these options are just related to the convergence criteria. It's just when is the system going to quit its iteration, but let's just leave it where it is for now. Now, we already found out the pressure at this downstream junction is 37.74. But that's if there's no demand. If we actually start taking water through the pipe, then the pressure could go lower. Like, think about in your neighborhood. If all of your neighbors were using water at the same time, what that does is it reduces your water pressure. And you've probably seen that at the airport. Like if you're at the airport filling up your water bottle, and then someone walks up next to you, to the fountain next to you, and then they start filling up their water bottle, what happens to your stream? Yeah, the trajectory is not as high. You kind of have to tip your bottle over a little bit closer, which is disgusting, right? So now the mouth of your bottle is closer to the dirty bottom. So the point is that when there's more flow rate going through a pipe, the pressure decreases. So let's test that out. Let's see how the system affects a change in demand versus pressure. So here under base demand, let's put in a demand. Let's say, now this is gallons per minute. What if there is 200 gallons per minute being taken out of the fountain? So what I have to do now is I have to click run, and let's see if it brings the pressure down. If the pressure goes up, we're in big trouble. Let's click run. Okay, and it updates the pressure. Now is 26.36. And so what it did just now is it used the Hazen-Williams equation, and so now it's saying the pressure at the fountain is the static pressure minus the losses that occur as the water flows through the pipe.
Why'd the head change?
The total head?
Yes.
Total head is just a reflection of the pressure.
Okay, so it's not one elevation.
No. The physical elevation stayed the same.
I was gonna say mine is not.
Let me pause the recording so I can look over your shoulders and see if things are working. All right, so on the back of the paper, I give you some instructions on what we need for today's lab. This is not a full report you're doing for today's lab. What you're going to do is go through these questions and just kind of assess, for example, how does changing the water temperature affect the situation? Or what if you have mercury instead of water is the fluid? Or how high do you have to take the reservoir elevation in order to achieve a certain pressure? You know, like if you are looking for the pressure, let me take the base demand back down to 0. Recalculate. So I'm back to my original pressure of 37.74. So what if I want the pressure to be 40? So how high does the reservoir elevation have to be to get a pressure of 40? So I could try, well, what about an elevation of 680? And I calculate, so I'll click on the run. And now we'll double check the properties at the fountain. So 39.71, so I'd maybe need to take the elevation a little bit higher. So basically this is just asking series of questions that invites you to explore how the program is running and making changes to certain parameters. And the way that you submit this is take screenshots of the program. So, for example, if the question is asking you to change the elevation of the reservoir, then you'd take a screenshot, like type in 600. Let's say we want to look at the elevation. Oh, sorry, that was the junction elevation. I've just changed it. It should be 588.36. So what if I change the reservoir elevation up to 700? Okay, so to screenshot, there's a button on your computer, the print screen button. It's usually up at the top right. Mine says PRT SCR. So if I push that button and then I go over here to Word, let's say I start a new document where I'm going to be working on my report. So, you know, problem 1. As shown in the screenshot below, I updated the elevation of the reservoir to 700 feet. Okay, now I paste that with my paste button, and what it pastes is the picture that I just screenshotted. By pushing that button, it kind of took a snapshot of what's on the screen. So I click on the picture, and I don't need to show the whole thing. Maybe I just want to show this particular dialog box. And so here under the picture format menu is a way to crop the image. All right, so I crop the image down like so, and then I can make it a little bit bigger just so it's easy to see. All right, so this is proving that I changed the elevation of the reservoir, and then the resulting pressure at the fountain with this reservoir elevation change was that the pressure increases to, now let's see, I've got it at 700, I run the model, and now I want to show the results. So I double click and bring up the fountain. I'll print screen again, and then this is what I'd paste into here, and the pressure looks like it's 48.37. So 48.37 psi. And then I could explain, you know, like if the question is asking, you know, explain the theory, The reason why the pressure increased is because the elevation difference, delta H, that goes into the hydrostatic equation is greater than the base condition when the elevation was set at the original value of 675.47. So this is basically how you're going to submit your report, is just a series of screenshots and short answers, basically proving to me that you went through the activity, showing the evidence of what was the input, what was the effect. So when you change a certain thing in the program, take a screenshot to show the change that you made, just like the little proof and what you tweaked, and then show the effect of the change. And so here maybe I would want to, just to make it more readable, kind of zoom in a little bit more just on the part that's relevant. I could show my network and the results. So that's it. There's no additional hand calculations that are going to be needed. There doesn't need to be like a conclusion or a method section. It's just answering each one of the 10 questions, and then you can upload the Word document or you create a PDF of it and submit that to Blackboard. Now, as I announced in my email that I sent on Monday, the report from last week's lab isn't due until 4 o'clock on Friday. So you've got till 4 on Friday to do the hydrostatics, and then this is due before your lab next Wednesday. Any questions before we go separate ways?
On the second